Hello everyone, I am Yashi. I am from IC Bangalore. I'll thank the organizers to give this opportunity to present about my work. This is a brief outline of my talk. I'll be talking about what are the emerging challenges to the standard model of cosmology, which is the lambda cold dark matter model. And with this, I will motivate for looking for extensions of the standard model, and that too in a modified gravity framework. Particularly, I would be talking about a scalar tensor theory, which is a generalized scalar tensor theory called Hondesky gravity. Following this, I will discuss my recent works during my PhD, which I have carried out in the framework of Hondesky gravity. And with this, I will conclude. So, we have a standard model of cosmology, which is based on general relativity and cosmological principle, and which very nicely explains a broad range of cosmological observations. And this is a 6-parameter models, which is built on 3 crucial ingredients: dark matter, dark energy, which is a cosmological constant, and inflation. However, as is also discussed in many of the talks from morning, that there are some emerging challenges to this standard model, often referred to as the tensions and anomalies in standard cosmology. So at the forefront of these is the Hubble tension, which is a discrepancy in the measurement of H naught arising from 2 observations. Mainly the 2 observations which are in strong discrepancy is the one SHOES, which uses the distance ladder techniques to get an estimate of H naught. And the other one is the CMB based measurements, which are based on assuming a standard model of cosmology, which is taken to be lambda cold dark matter model. Once you take the model and use the CMB data, you get an estimate of H naught, which is on a lower side. So to illustrate, if you plot the PDF distribution of an observable H naught with the mean values from the 2 observations and their error bars, you see that they don't overlap, in the posterior distribution. And to illustrate better, if you plot the difference of the observables with their mean values, the difference of the mean values and their sigma, you see that the mean value peaks around 5 sigma away from 0, indicating the strong discrepancy between the observations. Now there have been various resolutions models proposed to resolve the Hubble tension. So they could be categorized into two parts. First is modifying the early universe, and the other is modifying the late universe. The idea is that if you are proposing any model which is alternate to the lambda CDM model, the fit to the CMB should not be disturbed, because CMB is very nicely explained by the lambda CDM model. So, and what parameter of the CMB is actually most sensitive to the dark energy physics is this angular size of the sound horizon, which is very precisely measured by the CMB observation. And this is a ratio of the sound horizon at the baryon track, sound horizon at the time of recombination to the distance to the last scattering surface. Now, the resolutions that are based on modifying the early universe actually reduce the sound horizon, and which in turn leads to a large value of H naught. However, there have been studies which have told that such type of modifications alone are not sufficient to fully resolve the tension, and thereby there is the other option, which is modifying the late universe, which is again tricky. The idea is that you need a faster expansion at late times to explain a large value of H naught, which leads to a phantom type of behavior in equation of state, where the equation of state is less than -1, and this leads to a faster expansion. However, simple models like trivial phantom equation of state again is not favored by the data, because it alters the distance to the last scattering surface and thereby disturbs the peaks of the CMB. So there have been various studies which are based on parameterizations of equation of state and reconstruction of the dark energy properties from low redshift data. And these have indicated that the models where you have certain non-trivial features like phantom crossing, where there is a crossing in the equation of state of dark energy between non-phantom and phantom regimes, or if there is a negative dark energy at high redshift, or if there is a variation in the G effective, the effective gravitational constants, these features can help reconcile the data better in comparison to the standard model and resolve a lot of tensions. The point here is that all these non-trivial features actually cannot be realized in a general relativity framework, because they will lead to certain instabilities. And therefore, there is the need to go beyond general relativity, which is one of the core principles of the lambda CDM model, to realize these features and build the models. So this is the motivation for exploring the modified gravity theories. So there are certain other challenges, as already talked about, particularly the DAISY. So DAISY has found hints of dynamical nature of dark energy. But interestingly, what is also there is that in the W0 WA plane, or even if the reconstruction of the equation of state from the data, there are hints that there could be phantom crossing at high redshifts. That is, the equation of state of the dark energy goes in the phantom regime at high redshifts. If this is so, if this feature persists in the data, then one needs to think of what type of model could actually lead to such type of phantom crossing, which cannot be realized in a general relativity framework. Similarly, there is a study which found that when you set the growth index parameter free, even on the top of a lambda CDM background, there have been indications of suppression of growth rates. So using the data of the galaxy clustering and peculiar velocities, one can get an idea of the growth rate, how the growth rate of the universe evolved with the redshift with time. And even if at the background level the dynamics is very similar to GR, you can have differentiable effects at the level of the perturbations where you can see in the observables like growth rate. So this in the recent study has indicated that there is this indication of suppression of the growth rate at the very low redshifts. So all these things are indicating that maybe there is a possibility of looking for extensions beyond general relativity, and that is what is the motivation that I have explored in my first work. So we are trying to see that whether we can derive these non-trivial features like phantom crossing or negative energy density at high redshifts by a Lagrangian, by introducing some scalar field interactions rather than working with parameterizations, and can we do so in a theory which is free of any instabilities like ghost or gradient instabilities, and can we also address the Hubble tension. So this is one particular framework which is the Horndeski theory. It is a generalized scalar tensor theory of gravity. So it's a theory where the Lagrangian is constructed from metric tensor and a scalar field, including all sorts of possible contribution between the scalar field and metric. The point is the equation of motion always remains second order. So this was this Lagrangian was constructed by Horndeski, who was a student of Lovelock. This was his grad project, and now he is a famous painter. And these equations are actually interesting because they can accommodate a large number of modified gravity theories together. For example, you can work with Galileans, you can work with non-minimal coupling, non-minimal derivative coupling, quintessence, even GR, everything put together just depending on the choice of the coupling functions. So that's why this makes this generalized framework interesting for model if you want to explore the different types of models. And these are also interesting because there are codes, public codes, which have implemented these Horndeski theories so that you can also see the effects on the CMB and isotropies and do a nice model comparison with the lambda CDM data. Now, just the Jargon's equations here. So you have Friedmann equations and the evolution for the scalar field. And now the evolution in here, the rho phi is actually an effective term which has contributions arising from these non-trivial interactions that you introduce depending on the choice of the functions. There are also certain conditions that need to be kept in mind so that the theory is stable. That is, you avoid gradient or ghost instabilities and to make a consistent setup. So with this, I will introduce this first work which is done with my collaborator Basundhara Ghosh and my PhD supervisor, Professor Rajiv Kumar Jain. So here we explore Lagrangian where the dark energy is not a cosmological constant, rather a scalar field which has certain interactions like non-minimal coupling, Galileans, and a canonical kinetic and potential term. What this brings about, so you get an effective energy of state which could actually go to negative regimes at very high redshifts. The dark energy could become negative at high redshifts, as well as it could lead to a phantom type of behavior in the equation of state. So this is a subclass of Horndeski by choosing the different functions. The results are something like that. Here is how the expansion rate of the universe will change with redshift. The black one is the lambda CDM one, and the colored ones are the different for the data. We see that we can get a large value of H0 at z equals to 0 for different choices of model parameters, and a smaller value of the expansion rate falls behind lambda CDM at high redshifts. And what interestingly happens is that the energy density of the scalar field, which is the dark energy, is negative at high redshifts, but it transits to a positive value at present time. However, the total energy density of the universe always remains positive, so there are no pathologies in the theory. And this transition from negative to positive energy is also imprinted as this feature in the equation of state. And the late time dark energy equation of state could be phantom as well to resolve the Hubble tension. For the analysis, we included the data, the low redshift data in the first part where the BAO cosmic chronometers, Pantheon Plus and shoes were used, and we got a value of H0 around 71, which alleviates the tension a little bit so with this setup. However, this data did not include the CMB measurements. So this is what was the next work which is done in collaboration with Ujjwal, who is a PhD student at IISc, and Professor Rajiv. So the motivation here is that how the growth of structures, because now you are working in a modified gravity theory, one has to take care of how the growth of structures at late times also changes, because this could have significant effects in comparison to GR and could help to distinguish the underlying theory of gravity. And the effects on the CMB power spectrum as well are important because you are proposing a model as an alternative to lambda CDM. Then finally, this will help in a combined likelihood analysis to say something about the validity of model in comparison to the standard lambda CDM. For this, we implemented the code in a Boltzmann code and see the CMB anisotropies. Also, the effect on the growth of structures, why it is important, just to illustrate that, for example, the growth rate can be significantly deviating in case of non-GR theories. Here in the quasi-static limit, how the matter perturbations evolve, this equation is given here. The G effective in case of the GR is just a Newtonian constant. However, in a modified gravity theory, this could be a function of time. So that's why there could be significant deviations in the F sigma 8, which are crucial to consider. This is what we, these are the results for the model implemented and seeing the features in the expansion rate and the equation of state. So here the equation of state, again, one can go in the phantom regime or non-phantom regime depending on the choice of the coupling parameters. Similarly, in the growth rate, here the dashed one is what we expect in the lambda CDM picture, and here are the growth rate measurements in the model, which show a suppression, feature of suppression at the very low rate shifts. Finally, also see what could be the effects of potential effects on the CMB power spectrum. There could be shift in the peak because of the modification of the expansion history. And finally, we do a data analysis to find the best fit constraints on the parameters. When the data are taken separately, for example, the BAO, the Pantheon plus, when they are taken separately, we find that model can indeed allow a large value of H0. Similarly, when Planck data alone is taken, the model gives a equivalent fit to the data comparison to lambda CDM model. It also shows a preference of a large value of H0, the blue one, and a smaller value of S8, here the blue one, again for the model, showing that the model has the tendency to resolve the H0 tension. However, in the combined likelihood analysis, when we combine the low redshift and high redshift measurement, this is tightly constrained because of the non-overlapping regions of the parameter space, and we find that the model only leads to an extension to a large value of H0 that is not much of help, which is around 68. However, the interesting properties that the model has, for example, the phantom crossing and the negative energy density, are important in the light of these recent observations like DAISY and also JWST, which has seen some high redshift galaxies which are not, which cannot be formed in a lambda CDM picture. So this is the summary that we explored a dynamical dark energy scenario, and this shows interesting features like phantom crossing and negative energy density. However, we do not find that the models statistically outperform the lambda CDM model, but there are certain features which require further exploration. And I will just conclude with this slide that this particular class of non-minimal coupling model actually shows very interesting features because it can naturally give rise to phantom crossing type of features which are seen in the DAISY data. And there could be deviations in the growth rate as well because this is a modified gravity theory. There could be scale dependent effects which could be probed with the galaxy LSS data and could help us to probe the deeper nature of dark energy by looking at the effects on the perturbations. So yeah, that's all. Thank you.
I had two questions here, Heshi. One is you talked about stability and speed of sound of the perturbations and so on. But in that particular slide 12 or something, you had, the primordial perturbation, the curvature perturbations. But in the context of dark energy, I don't care about that, right? I need to know what happens to something like P by rho or P prime by rho prime at later times.
These could be related to the scalar field perturbations at late times, right?
I will not talk about curvature perturbation at late times. I will talk about what you had later, psi and phi.
Yes, yes.
So you will look at P prime by rho prime, whether it is positive or negative. So this constraint, you can, since later you're considering them generated during inflation, I am sympathetic, but it's not valid, necessary at late times.
I think I have the slide because the first part was on inflation, but what I meant is the sound speed of the scalar perturbations in the late time.
Okay, so I don't know what you do at late times. How do you ensure? Is P prime by rho prime positive at all times?
Yeah, CSS squared should be positive at all times. CSS squared.
It depends on what is CS squared.
So
that CS squared is different from
yeah, for
the
that,
CS squared I'm talking
yeah,
about.
delta rho, P by delta rho for the scalar perturbations, that should be ensured to be.
That is not that C squared.
No, no,
CS
that's
squared.
what I think here it's for the inflation part, because the slides are from the inflation
Okay.
part. What I meant is the perturbation speed for the scalar components be positive all the time.
And in one of your slides, you had a W of phi or something as a function of Z, and there were so many spikes.
Okay, here,
There one.
yeah.
Why are these spikes arising?
These spikes are arising because the energy density of the scalar field was negative at high redshift. It transits through a positive value at very low redshifts. So the spike is just an indication of the transit from negative to positive value of the rho of phi, which is the dark energy.
And your speed of sound is well behaved across all of them?
Yes, it is. For this setup, we ensure that it is well behaved, it is positive and real throughout.
Okay. Okay.
No. This is for different choices of the parameters. These are for different. It's showing that where this crossing will happen will depend on the strength of the coupling.
After all that effort, chi squared, delta chi squared is 0.6.
It's 0.6, yes.
Okay.
Yeah. Yes, that's what this Hondesky type of models give you, that the effective equation of state goes to a phantom regime. So instabilities like ghost instability, which will arrive in a simple phantom scenario, could be avoided by adding some effective terms which are arising due to non-trivial interactions of the scalar field with gravity or itself.